Hello everybody and welcome. Today I want to do a review of some basic math ideas, add, subtract, multiply and divide, all that kind of stuff, what's the number and so forth. But I want to talk about not just the computations, but the ideas behind them, kind of as a pre-algebra sort of a thing. So get some paper and pencil, because thinking and writing should always go together. And let's just go through a couple of questions. Let's see now. I need to share my screen with you. You should be able now to see my screen. So, a couple questions. Number one, how tall are you? I am, about 5 foot 10 inches, maybe five, a little more than that. Maybe I can sneakily say I'm 5'11", but yeah, about 5 foot 10 inches. How many people are in the room? Well, that depends. Like, right now it's just one because it's just me. I'll go ahead and put one. Maybe if you're in a classroom or something like that, you might, include like the number of the students, including yourself, also including the teacher, right? Because the teacher is a person too. Number three, write the number using symbols, 5,604. So that would be 5,600 and then no tens and then 4. How did that work for you? You certainly have a height. Maybe you gave it in centimeters or something like that. How many people are in the room? You certainly can be able to count, right? You can count. And then you wrote the number using Western symbols there. Obviously, we're in English, so we're using the English system here. Let's talk now about what some of these things mean. Number, let's do notes now. Okay, number actually tells us two different things. It tells us the size of a single thing, in other words, how big. It also tells us quantity. Quantity would be how many? Now this is crucial. I asked you two questions. How tall are you? Does that tell size or does that tell how many? Does that tell quantity? The first question addresses size. The second question addresses how many. Okay? There's two different kinds of number systems. One of them tells how big something is. The other can be the same kind of a number, but the number tells how many of a single thing or how many of a thing that there are. This gets into this concept of a one and a many, which has got some profound philosophical connections, right? If you know anything about American history or culture, the motto is e pluribus unum, out of many people, one nation. How do you balance the rights and needs of the one versus the rights and the needs of the many and so forth? That's an interesting conversation, and it involves more than just maybe mathematics. Also, size. Size would be a continuous number. Once you start dividing it, you can divide it kind of infinitely. All right. So if I said how tall are you, and let's say that I was maybe 5 foot 9 inches at some point in my past, and then I grew and I became 5 foot 10 inches. Didn't I have to hit 5 foot 9.5 inch somewhere in there, right? I don't just jump over the in-betweens, right? I've got to hit every single thing that's in the middle. It's a continuous kind of a numbering system. All the in-betweens count. But quantity often is a question of a discrete number. And a discrete number is one where there are no in-betweens. So how many people are in the room? 1. If somebody else comes in the room right now, I would say, well, 2. At what point did I have 1.5 people in the room? Never. So quantity oftentimes is a discrete concept. There's no in-between. So continuous and discrete numbers, those are kind of some of the basic fundamental ideas about what number tells us. Size and quantity. All right, now let's talk about the number system. The number system that we use has the symbols. We use a base 10 numbering system. In other words, when we get to 10, we start to regroup. There are other bases, like computer uses binary language, which is base 2. Sometimes there's base 6. Sometimes there's base 8. Why do we use base 10? It's really kind of simple. Think about how humans count. You got 10 fingers, okay? Hopefully. We use a base 10 system because this is when we start to regroup, right? And so we use a base 10 system. You can use other bases. We use the symbols, starting with the 0, which is an important concept. Some cultures don't have the concept of 0. It was crucial for 0 to be understood as an actual quantity. Nothing as a quantity takes a bit of an understanding. But 0, and then 1, and 2, and then 3, 4, 5, 6, 7, 8, 9, and then we're out of symbols. At 10, we start to regroup, and we use spaces. 1, 0 means 1, 10, and no ones, right? Remember the place value system? Remember this? This would be the ones, this would be the tens, this would be the hundreds, this would be the thousands. We could keep going. There's actually families, right? This is the 1,000s, and then over here would be the 10,000s, and then over here would be the 100,000s, and then we start to regroup again. Our number system is positional. If I did not put a 0 right here, and I just wrote 564, that would mean a different number than 5,604. It would mean 564. I have to put a 0 there to hold that space. That's going to be crucial later on in algebra. Be careful with your symbols, particularly 4s and 5s and 6s. A 4, let me zoom in here, a 4 has a corner on the end, and it intersects the stem in the middle. This is a 4. This is a 4. Notice it's got corners on the ends there, and it intersects the main stem in the middle. This is not a 4. That is a Y. And you're going to have to be clear how you write your 4s and you write your Ys. I will not accept this as a 4. It isn't. I had a student one time who the answer was 4Y, and he wrote that. I said, 44? He said, yeah. Oh, no, wait. He said, no, why? And I thought, why? Good. That was a good thought. Why? If you write your 4 to look like a Y, I will ask you, why, W-H-Y, why did you write a Y? Be careful. 5 and 6. This is an S. Notice my S is curvy. A 5 has to look fundamentally different from it. My 6 has got like a swooshy kind of a thing here. A B is a straight bar that comes down and then comes around like this. You've got to be able to look at these symbols and tell them apart. Write them neatly. Now, interesting thing about algebra is algebra just comes over here and says, well, I don't know what the base is, right? Isn't algebra the mathematics of unknown numbers? And the first number that we don't know is maybe the base. So when you did normal algebra, it was like, this was like 10 to the first, right? This was like 10 to the 0. This was like 10 squared. Is it 110 squared, right? This is now 10 to the third. If I do place values, it's just like that. But now what if I don't know what the place value is? Well, this is going to be x cubed, and this is now going to be x squared. This is now x, and this is now x to the 0, although you commonly don't write it that way. So what if I said this? What if I said 5x cubed plus 6x squared plus 0x plus 4? What I've got right there is a polynomial which is identical in structure to this number right here, base 10. Except, we don't know what the base is. We're gonna get to this sort of a stuff. We're gonna start to do math of unknown numbers. Okay, enough of that. Now, plot +3 and -4 on the number line. Well, I first have to find a place where my sign changes. I'll call that 0. I'm just going to pick a point right there. I'll call that 0. So this is 1, 2, 3, 4, 5. And on the left-hand side now is -1, -2, -3, -4, -5. Plot +3. It goes on the line. Don't draw it above. If you draw it up here, you're plotting something else besides what we're asking you to plot. This is a number line. The points lie on the line. Do not write it above the line. So +3 in there, and -4 is right there. Okay. Now, number 5. 3 minus 5, that would be -2. 6 would be 10 plus a -7. I'm going to change these signs into 1. When I see two signs, I'm going to change them into 1. 10 minus 7, 3. 6 minus a negative 9. Well, again, change the signs. What's a negative times a negative? A positive. So this becomes 6 plus 9. That's 15. Negative 2 times negative 8. A negative times a negative is a positive. So the answer is positive. And then the numbers 2 times 8, 16. Okay? Now let's go back and talk about what these mean. We've made a shift now over to sign. What does sign tell us? Sign tells us direction. I've been around math a long time, did physics for a while, and it was actually physics that helped me understand this. The only purpose of a sign, positive or negative anywhere, is to indicate some kind of direction. The number means the magnitude, right? Like negative 3, the 3 tells you how big, or the 3 tells you how many. That goes back to number, which was the previous note point. Sign tells you direction. The very first thing we do about sign is we understand that it means on the left or the right side of 0. So if I come back to a number line, really the positive side is 0, plus, 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 plus. The negative side of 0 is on the left. So the sign tells you the direction of the position from 0. Okay? So sign tells you direction. It can, number one, be the property of the number itself. So the sign can be a property, like I did with these right here. Okay, positive 3, negative 4. But sign can also tell you change. Okay, so property. Property would be which side of 0. Change, though, is the direction from one number to another. So you're going to be moving to the right, which is a positive change, or moving to the left, which is a negative change. I could start here at, let's say, positive 5, and I could move to the left to 3. That's a change of negative 2. Now notice it doesn't involve, it doesn't involve this negative 2 at all. I'm not talking about the position negative 2. I'm talking about the change to the left 2 units. Okay, so what's going on here? This says starting at 3 and then moving left 5 units. And so if I start at 3 and I move left, 1, 2, 3, 4, 5, what do I wind up with? Negative 2. Okay, so it also shows change. Now let's talk about combining of signs. Let's make a break in here. Combining of signs. If you're doing sign numbers, there's lots of different ways people have learned this. This is the best way that I can do it. First thing, are the signs the same? If the signs are the same, what you do is you add the numbers and you keep the common sign. So, for example, if I said positive 3 plus 2, are the signs the same? Yes. Add the numbers. Which 3 plus 2? 5. And the sign is what they both are, positive. If I had both signs negative, negative 4 minus 5, are the signs the same? Yes. Add the numbers. What's 4 plus 5? 9. Keep the sign that they both are, negative. Some people will say like, oh, don't subtract a positive, add a negative. Like, I still don't understand what does that mean? I don't understand that. So my rules will be, look, if you're combining sign numbers, which is really adding, you're adding negatives in a sense. But are the signs the same? Add the numbers. Okay? Next idea, the signs are not the same. Signs are different, D-I-F-F-E-R-E-N-T. If the signs are different, guess what you do? Subtract the numbers. And then you're going to keep the sign of, of the larger original. That's kind of a long way of saying it, but if you look over here at, let's see here, look over here at this example right here. Once I get to this point, the 10 minus 7, are the signs the same? No, because the sign on the 10 is a positive, even though it's not written there. Are the signs the same? No. What do you do with the numbers? Subtract them. What's the difference between 10 and 7? Don't worry about positives or negative, just what's the difference? 3. Keep the sign of the larger number. Positive 3. If we were doing something with a negative sign, let's maybe say it was, let's make it positive 5 minus 8. Are the signs the same? No. Find the difference between 8 and 5. What's that difference? Just the bigger one minus the smaller number. Don't worry about the sign. 3. But what's the sign of the larger original number? 8 is larger than 5, so I've got to have leftover negatives, negative 3. Okay, so if the signs are different, you're going to find the difference and keep the common sign, or keep the sign of the larger original. Okay, and then you probably know that when you multiply now, getting down here to this, if you multiply a positive times a positive, whoops, I didn't mean to draw a circle, times a positive is equal to a positive. A positive times a negative is equal to a negative, and a negative times a negative is equal to a positive. Why? Why does a negative times a negative equal to a positive? Well, what does the sign tell you? Direction. What does a negative tell you? Opposite. What's the opposite of an opposite? The original, right? If you stood facing north, wasn't that a song by R.E.M.? Stand in the place where you live. Now face north. If you face the opposite direction, you're facing south. But then if you do the opposite of that direction, you're back to facing north again. See how they cancel each other out? Okay. So this would then be a negative times a negative would be a positive. That would then give you an opposite. This is for multiplying. And we're only going to use parentheses now when we multiply. Please do not use x as a multiplier. Not using x. All right, so now addition. Add this to that. You know, I don't have that answer memorized. You probably know a method where you bring the 534 and put it down here, 534, and then you add up the columns. And you do have some basic things memorized. You should know what 2 plus 4 is and 1 plus 3 is and stuff like that. So now I'm just going to add up the columns. 2 and 4, 6. 1 and 3, 4. It's actually not 1 and 3. It's 10 and 30. It's 110 and 3 tens, which is 4 tens, which is 40. But if you put the number in the proper position, the place value takes care of itself. See, you don't even have to think about that. And then 3 plus 5, which is 8, but actually we're adding hundreds, and so there we go, 846. You're going to line up the place values. When we do this in algebra, you're going to do the same thing, but you're not going to know what the numbers are. Okay, so what is addition? Let's talk about that. Addition is combining parts to get a whole. So you've got this idea. You've got a part plus a part, and then afterwards you've got a whole. So if I had 3 pumpkin pies and I made 5 more pumpkin pies, I would have 8 pumpkin pies altogether. Okay, the 3 and the 5 are the part, the 8 is the whole after I put them together. I like pumpkin pie. So now, moving on, how about subtraction? Subtract 139 from 752. The order matters, and sometimes the order when we speak is different than the order symbolically when we do it. Did you catch the mistake I said? Subtract 752 from 103? No, that's the opposite direction. I need to subtract 139 from 752. So I'm going to write 139 underneath, 139. And now I'm going to subtract, and now I can't subtract 9 from 2, so I borrow. Basically, I'm regrouping. I'm taking a 10 out of this and saying, hey, I've only got 4 10s left there. But I'm putting a 10 in there, so now I've got a 12. 12 minus 9, 3. And then 4 minus 3, 1. And then 7 minus 1, 6. Remember how to do that regrouping? We don't regroup in algebra because we don't know how many go in each group. So there will be no regrouping when we subtract polynomials. You're so happy. Okay, so now subtraction. Subtraction, I'm going to say that's removing a part from the whole with a part remaining. And maybe the part remaining is 0, right? Because 0 is also a value, okay? Now, order matters. Be careful which thing you're subtracting from the other thing. If I said 9 minus 4 is equal to 5, the 9 is the whole, the 4 is the part that I'm removing from it, and 5 is the remaining part. Okay, so be mindful of the structure there. Order matters when you subtract. All right, now let's do multiplication. 467 times 52. Now maybe you're thinking, oh, 467 times 52. But remember I said we're not using x as a multiplication symbol ever. Well, we'll do it once because we have to, but I don't want to talk about that right now. So we're not going to use that symbol. Use a dot, or even better would be parentheses. 467 times 52. Sometimes a dot can be confused as a decimal. But in any case, you probably don't have the answer to that memorized, but you do have a method. So you're probably going to take 52 and write it underneath. Remember, lining up the place values, and now you're going to multiply. I will put a circle around it so that you know that it's not a variable. Anyway, 7 times 2, 14, carry the 1. 2 times 6 now is 12, plus the 1 is a 3, carry the 1 on that one. 2 times 4 now is going to be 8, plus the 1, I'm getting 9. So 467 times 2 is 934, and now do you remember what you do next? You put a 0 right there, right? Why? Don't put an X there, you put a 0 there. Why is that? Because now we're done with the 2, and I'm moving over here to 5. But it's not 5, it's 50. It's 5 tens, and we're multiplying by tens. And so we've got to have that 0 there to hold the place value. So now 5 times 7 is 35. Done with that, write a 3. 5 times 6 is 30, plus the 3 is 3. Scribble that one out, carry another 3. 5 times 4 is 20, plus a 3, 23. And so now I'm going to add them all up. I get a 4, an 8, a 12, carry the 1, that's a 4, and that's a 2. Let's put a comma there. There we go. Okay, did you get it? Good. When we multiply polynomials, we'll use the exact same structure. Okay, what's multiplication? It is repeated addition. Adding the same thing multiple times. Okay, so it's adding groups with the same number of elements in each group. There's your key word, is each. So if I said 2 times 3, that's 6. Really what that's saying is that I could go 2 plus 2 plus 2, 6. Okay? I'm adding together 3 groups of 2 with 2 in each. Or you could say it's even 3 plus 3, 2 groups of 3. That's also 6. Okay? So one of the things in the problem, this one is either the number of elements, and the other one is the number of groups. Whoops, that's supposed to be a U. Or vice versa. Okay? This in the end, these are called factors, if you remember. Factors are things that are multiplied. Factors. This right here, that's a product. You're going to have to factor algebraic stuff, right? Remember, what you're doing is you're separating into things that are multiplied. Okay? So use a dot or use parentheses for multiply. Don't use an X. All right, division. I'm going to do long division here. So I'm going to rewrite 94. This is the dividend This is the divisor. If you remember your little thing, you put the 94 in the house, and then you write the 4 over here. And then I'm going to go, how many times does 4 go into 9 without going over? That would be a 2. Now, 2 times a 4, that would be an 8. And now I subtract, so I get a 1. And then I bring down this 4, that would be a 4. 4 into 14 goes what? Oh, I wrote the problem down wrong. Hey. I'm going too fast. 7. So that's going to be 7. 4 into 17, that goes 4 times. That would be a 16, subtract, I got 1 remaining. How do I write that? This is going to be the answer, 24 plus 1 over 4. I don't do mixed numbers. Write a plus in there if you need to. We'll talk about that a little bit later. Okay. Order matters when you divide. Okay. So what's division? If multiplication is repeated addition, division is repeated subtraction. Okay. You're subtracting groups with the same number in each group. And so what it really means is you've got the whole divided by the group, the number of groups, and what you get then is you get the number of elements in each group. Okay, so if I said 97 divided by 4 here, what I'm saying is I got 97 things. How many are in each group if I make 4 groups out of them? Well, there's 24 in each group, but I got 1 left over. Okay, or it could be the other thing. This could be the number of elements. And this could then be the number of groups. So if I take 94 things and I want them 4 elements in each group, how many groups do I have? I got 24 groups altogether, and I got 1 left over that doesn't go evenly. Okay, now let's do an exponent. An exponent means the cube here means it's going to be -2 times -2 times -2. That's going to be -8. The thing that you take the exponent of is called the base. And this then is called the power. And the answer is called, no, I'm sorry. Stop, Marsh, you made the mistake. I'm thinking ahead. This is the exponent. We've got to be very deliberate about our language. The answer is called the power. Sometimes the exponent is mistakenly called the power, but it's not. It's the exponent. So, what's an exponent? It's repeated multiplication. The base is the thing that is repeatedly multiplied. How do I say that? The exponent tells you not how many times you multiply. The exponent tells you how many bases. That's a subtle distinction. And we'll talk about that maybe a little bit later. Okay, keep it going. Oh no, a radical. Well, okay, so there's a number of different ways to approach this. Here's how I want to do it. I want to say that it's the square root of a 9 times a 5. I want to factor 45 into things that are perfect squares. Why is that? Because I'm doing a square root. I could do a cube root, and then I would be looking for cubes, but I'm not. I'm looking for perfect squares. So this now becomes the square root of a 3 times a 3 times a 5, if you want to think about it that way. And then maybe you've seen this before and maybe not. There's a little number that goes right here in blue, in the little crook of the square root symbol. That's called the index, and we'll talk more about that later. For a square root, it's 2. For a cube root, it's 3. But you don't write it for 2. It's kind of understood, right? If it's the square root, you don't have to write the 2. But if it's a cube root, then you have to start writing what it is. What this means is, can I take out a pair of factors? Yeah, a pair right there. So when they come out from under the radical, I'm left with just 1. This is 3 then times the square root of 5. Or you can think about it this way. The square root of 9 is 3. and then what I've got left is the 5. Okay, so 3 square root of 5. What then is a root or a radical? It's repeated division. And so you're going to have the symbol, the index would go right there. The thing that's inside is going to be the radicand. And we'll do some more of that. Okay, got to finish up here because time's short. Simplify as a fraction. I'm going to do this a little bit differently maybe than you've seen it before. I'm going to go ahead and write it like this. 7 times 3 divided by 7 times 5. And look, I get 7 over 7. What is that? What's 7 divided by 7? 1. And so my answer then is just going to be 3 over 5. You might have been able to see that without writing it out like I did, but when you do algebra, you won't be able to, so you'll have to factor it, okay? So what is a fraction then? Let's talk about that. A fraction is a keyword equal part of a whole. Don't just say part of a whole. All the pieces have to be equally sized, okay? So you've got a numerator, you've got a denominator. The denominator is the most important part. It tells you how many equal parts make the whole. And then the numerator is just how many parts you got. Okay, so let's talk now about operations. Subtraction. Oh my goodness, look at this. The first thing you should notice is that I don't have a common denominator. I have to get a common denominator. What's the common denominator? It's going to be 84. We will talk maybe about how to do that later. What do I need to do to make a 12 and 84? I need to multiply 12 by 7, which means I have to multiply the top by 7, right? Because what's the value of 7 over 7? 1. And I'm allowed to change the form of the fraction, but not the value. So I'm multiplying by 1. Excuse me. 7 times 5 now, that becomes 35. Minus, what do I multiply 28 by to give myself 84? I think that's 3. So multiply this top by 3. So there we go, that's 9. Now notice I've written it all over a single denominator, and I'm doing just my operation on the numerators. That's crucial. There's the bell. I need to hurry up or I'm going to be late. So this is now 26 over 84. But that can be reduced now to 1342. Okay, you're going to have to get a common denominator and then reduce after you do the operation. Okay, multiplication now. Look, 2 fractions. Well, here's what I can do first before I ever multiply. Now, normally when you multiply, you would take it straight across here and call it 10, and you would take this straight across, and oh my goodness, what is that? I can't do that real fast. But when you multiply, you actually can simplify before you do the multiplication. So any factor in the top can cancel with any factor in the bottom. This is just like one single fraction. Oh, look. I got 5 and 15. It's going to be 1 and 3. Oh, look, 2 and 18. I got a 1 and I got a 9. Does anything else cancel? No. Now I just take the things I've got and come across 1 over 3 times 9, 18th. And then I never had to reduce. You're going to have to do that with algebra because you can't reduce after you multiply everything out and make it really, really big. You're going to have to reduce first and then multiply. Okay. Now, one last one, solve the proportion. Notice all of these are fractions, and it's the sign in the middle that tells you what to do. Well, okay, looking here, if 3 multiplies by 2 to give me 6, wouldn't this equal to 14 right there? Maybe you see that directly. But here's an interesting thing about proportions. Proportions are 2 fractions that are equal to each other. Here's what's true. If I take the diagonals and I multiply them together, 7 times 6, 42. Guess what has to happen if I multiply these together? 3 times 14, 42. 42 is the answer to everything, right? So now this is going to be, this is the property of proportions, that the cross products have to be equal. So how do I solve it then? I solve it maybe by putting an x right here, and then I just set the cross products equal. 7 times 6 has to be equal to the 3 times the x, and then you just solve it algebraically. Okay, so fractions tell us then, where's my notes? Come on, here we go. The numerator and the denominator. Fractions also can tell us a ratio, and I'm almost done. It's a comparison between two different values. So maybe I have like the ratio of males to females in a class or something like that. It's a comparison. They're not the same thing, but it's going to be one value over another value. One thing compared to another thing, something separate. Like in automobiles, isn't there like a thrust to weight ratio, right? How much power you get versus how much weight you've got. I know an aircraft, that's one of the ratios we're going to do. Okay, so we're going to do all of these with unknown numbers, because that's what algebra is. So, go back and rewatch it in certain points if you want to, and ask me questions from time to time if you like. It's important to understand what numbers are and what we're doing with them. Numbers tell you either how big or how many, and signs tell you direction. And then from there, all the rest of that sort of sorts itself out. Okay? May your days be merry and bright, and may all your mathematics be right.